Hi, this is the video about inverse functions. We didn't spend much time on this concept, but it has many aspects, and hopefully this video will help you connect them all into a single big idea. So let's look at the function y equals f of x. In short, inverse function just swaps x and y. Call x y, call y x, and that's inverse function. So I'm going to rewrite that. As I said, but it won't be the same function anymore, so I'll call it g of y. I just swapped x and y around. So this is already inverse function, but it doesn't look much like a function. I mean, we usually write y as dependent variable and x as independent. So all I do, I just rename them. Another notation, actually, if inverse function has a special notation, and instead of writing just new name g, we are writing f minus 1 x. Don't mix it up with the reciprocal. 5 to negative 1 is 1 over 5. But when minus 1 applies to a function, then it really means inverse function. So let's see what happens when we switch x and y. What happens to all representations of functions? Let's have this big idea like really here in the front. So x and y swap around. That's it. That's what makes inverse function. Okay, so let's look at different representations. Consider a simple function y equals x cubed on this little part of its domain. X, y. Let's look at the table. So let's do 1, 2, 3, and that's enough. Cubing 1 is 1, 2 cube is 8, 3 cube is 27. So the way we look at this function normally, this is x cubed. But if you're going to look at it backwards, that becomes the inverse function, which will be, so if this function is f of x, then this function will be f minus 1 of x. And think, if you just rename x and y, we will get this, x equals y cubed. This is already inverse function, but we need to rewrite it in traditional form, so we'll need to uncube both sides, and this is a cube root function, which you could guess right away. The function, the inverse function, really is undoing what the original function did. The first function cubes everything, the inverse function uncubes everything. This was a first representation, table. In a table, the columns just switch. Let's look at the second important aspect of a function, domain and range. What's the domain of the original function, f of x? I'm going to only look at the domain in this little example. So domain is 3 numbers, 1, 2, 3. What's the range of the original function? Again, only on this little interval, little set. The range will be all values that the function takes after being applied to 1, 2, and 3. So this is 1, 8, 27. Okay, now let's look at the domain and range of the inverse function. When you go backwards, we start here and end up here. So the domain then is this, and the range then is this. In other words, domain and range switch as well. So this range of f minus 1, and this is the domain of f minus 1. Nothing strange. If x and y swap, once again, then domain and range swap as well. All right, next. Let's talk about graphs. So the graph of y equals x cubed. 0, okay, 0 is not really part of my domain. It should have been, but I'll graph it anyway. 1, 1, 2, let me label this. 2, 8, and 3, 27. Okay, it's not drawn to scale. Actually, I can draw it like somewhere around here. These are my 3.5 points. I'll connect them just so you could see better. This is my f of x, y equals f of x graph. Now, I'm going to graph the inverse function. So what? Let me label this coordinate so you could see better. So this is 2 comma 8. This point is 3 comma 27. What happens when I swap x and y? Coordinate swap. So I'm going to use different color. So 1 and 1 swap doesn't matter. 2 and 8 does. So it becomes 8 comma 2. So 8 is now here and 2 is somewhere around here. And then instead of 327, we graph 27, 3, which is somewhere far away there. 27 comma 3. And if you connect them, it will be something like this. So it will look better if you graph it on a calculator. You do know the equation, so this is inverse function, which is the cube root. But what happens when you swap x and y? It's kind of the axis swap as well. So x-axis becomes the y-axis and vice versa. 2, 8, 8, 2, the entire graph reflects. They reflect over this line, which is the line y equals x. This is the line where y and x are equal. And everything reflecting over this line, that what happens. X and y switch their roles. So, big idea. The graphs of inverse functions are symmetric with respect to the y equals x line. And let's write it down. Graphs of inverse functions are symmetric with respect to the line y equals x. And again, this idea comes intuitively even from this big key idea that x and y swap. Let's consider a slightly different example. Y equals x squared function. And the graph of it, as you know, is a parabola. Here it is. All right. So as we just learned, the graph of the inverse function will be reflected over this line, y equals x. So instead of the y-axis being the axis of symmetry, the x-axis will be the axis of symmetry, and my parabola will look something like this. But there is a big problem here. Do you see it? So we want this to be the inverse function, y equals f minus 1 of x. But the truth is that this is not a function. Remember why? It doesn't pass the vertical line test. Lines drawn vertically will cross this line twice, which means that pretty much all x values will result in 2 y values. And that makes it not a function. And why did this happen? Because the original function had 2 x's corresponding to the same y. So the original y equals x squared is a function, but we call it not one-to-one function. 2 different x values result in the same value. So it's 2 to 1, not 1 to 1. So in order for a function to have inverse function, it must be function must be 1 to 1 to have the inverse function. Otherwise, the inverse will not be a function. So we really want the inverse function. We really need to undo y equals x squared, and we kind of know that undoing square will be unsquaring, which is the square root of x. The truth is that only this part is square root of x, and this part is minus radical x, but both of them together cannot be in one function. So to resolve this issue, we are going to erase this part of the function, of the domain. And then we won't need this part of the graph. So what we have now is actually a one-to-one function. Every value is taken once. So this is y equals x squared when x is greater than or equal to 0. That's how our function is defined. And the inverse function is y equals square root of x. The range of the original function was y equals greater than or equal to 0, and they switch and they're the same, so it's the same range and domain for our inverse function. And yeah, they're both in the first quadrant, so no surprises here. Okay, so one more thing to do about inverse functions, and this is how you find the equation of inverse function algebraically. Okay, so let's consider two methods to find the inverse function. First, first of all, in order to switch the variables, and remember, this is the key again, x and y swap. That's all we need to know, really. We need to see both variables, so replacing f of x with a y, now we can swap them around. So call y x, call x y, and everything else stays the same. So this is already inverse function, really. All we need to do is isolate y. So we add 7 to both sides, so it's x plus 7 equals 3y. And divide both sides by 3, we get x plus 7 over 3. Or we can write it as x over 3 plus 7 over 3. Either way is fine. Second method. So that was 1, that is 2. Arrow diagram method. So you start with x and you ask yourself, what operations did the function f do on x? So what did it do to x? First, the original function took x and multiplied it by 3. So I'm drawing my first step. So times 3. And then it subtracted x minus x. And I got the y. So then the inverse function came and she said, oh well, I don't like that. Let me go back. This is not y anymore, it's an x. So I'm going backwards. I'm undoing everything. Instead of subtracting, I'm adding 7. Instead of multiplying by 3, I'm dividing by 3. And now, instead of x, I'm going to get y. All I need to do now is write down what I did, my process. I start with x, I add 7 to this, and then I divide everything, what I just got, by 3. So you see you got the same result. Look at the screen of a graphing calculator. This is a really easy way to check if your algebraic work is correct. So the original function y equals 3x minus 7 is this. My wannabe inverse function is this. And I also draw the line y equals 7, y equals x as my line of symmetry. So it's easier to see what happens. I also used a little trick. I press zoom 5. So I use zoom 6 first, but then I use zoom 5 on top of it, and zoom 5 equates the axes. It makes scales the same vertically and horizontally, so it's easier to see a symmetry. Now suppose you made a mistake and instead of x plus 7 over 3, or instead of x over 3 plus 7/3, you did, let's say, 7/3 plus 7. Let's say you forgot to divide by 3, which happens. And so this is the graph you would get. So this is the original line, and the new line would be this, x over 3 plus 7. As you see, they're not symmetric. If you cannot see it, maybe you want to draw this line again, y equals x, and you will see that it's not a line of reflection. So people make mistakes, but knowing what you expect from the inverse functions can really help you to check yourself easily. Let's look at one last example. This is the harder function, and we want to find the inverse equation of the inverse function for it. First step, as usually, we want to see the y instead of f of x. In this case, the arrow diagram won't help, because if you want to start with this, what happens to x first? Couple things happen at the same time. We subtracted 2, we added 1, and it's not easy to show with an arrow diagram. So we are going to use another method, which is we need to replace x and y, swap them. So we call this x, we call this y, we put it in both places as y. And guess what? This is inverse function. Wow. We don't see it, so we really want to isolate y. But how do you do it? Y appears in two places. So we want to get rid of this fraction. We want to multiply both sides by y plus 1. One way to do it would be to look at this as a proportion. Or you could actually say, okay, I'm going to multiply both sides by y plus 1. But I think it's easier to do as a proportion. So we cross multiply. We have x times y plus 1 equals y minus 2. So we accomplished not much, but at least they are all on the same level. And now if you distribute, we see that y appears in two places. And again, our goal is to isolate y. So it will really help if both our y's will be together, next to each other. Which side I want to do it? I could subtract this y from both sides, and then subtract this x from both sides. But then everything on this side will be negative, and I can avoid it by subtracting xy from both sides. So minus xy minus xy. So we have x equals, I'm going to also add 2 to both sides. So it's x plus 2 equals y minus xy. I'm almost there. I can factor out this y now. And this is like a key moment. That is why I did all of it. Originally my y was in two places and I could not put them kind of in one place. But now, instead of y in two places here, here, I can factor out y. And that's what I want. I need just one y. So it will be 1 minus x plus 2. And finally, I'm going to divide both sides by 1 minus x, and this is my answer. This cancels, so it's x plus 2 over 1 minus x. Do they look inverse? Nah, not really. But we can also graph, check by graphing. These are not really simple functions, but we can use graphing calculator. And this is what we are going to see. So I actually don't remember which one, but one of the functions is this. The other function is this. And again, I added y equals x line. And again, I use the squared zoom, which is zoom 5, in order to see the symmetry better. So yeah, it does look good, even though it's really weird. So if you go over all the ideas of this video, you will see there are many of them. We talk about graphs being symmetric, we talk about domain and range swapped around, we talked about switching x and y when you work algebraically. But all of these ideas actually come from one big key idea. X and y swap around. That's what makes inverse functions. That's it.